Welcome to these exercises on building a working parser, which will end up building the JSON parser. I will now give you a small orientation about what's in the code. There is a detailed instruction in this PDF file. I do encourage you to read it carefully before solving the stuff, and also encourage you to read the chapter. I endeavor to create as streamlined exercise file as possible. I hope you will appreciate how easy to follow it is comparing to how complicated the story in the chapter is. So let me create a copy of my repository so that I can demo it for you. We are in JSON. Let me open an editor. Increase the font. Okay. So I will solve exercise 1. In a moment I'll explain the exercise. But first I'll give you a small orientation about what's in the code, and then I'll move on to the exercise. Okay, my tests are running now. Let's see what will come out of it. All code that is relevant for us is in a single file. It's called the same as last week. It is in fact a variation of the last week's file. It's called parsers.scala. There is a corresponding spec file that I also encourage you to use. Of course, we have 68 tests. We have 70 tests, and 68 of them failed because exercises are not solved. And there are some that are testing the code that is already in the sheet. So that's why there is 2 that are passing. Okay, so everything is wrapped here in the object exercises. We have sort of 3 parts. The first and the most important part is the trait parsers. Trait parsers implements the API for parsers, assuming some implementation of parse errors and some implementations of parsers, the actual algorithm that advances the parsing. So this is the abstract design. Like last week, nothing is changed here. Inside this abstract class, the trait, we also have the definition of infix operators, this part here, right? I added a few so that they are in line with my slides, and the definition of laws, which are all the tests we could have written in this abstract part without actually having an implementation, because these are tests that are only test relationships between the API calls. So this is ending the trait parsers, and here we are in part 2. In part 2 we implement a concrete parser. There is a few types here. The concrete type parser, an implementation of a parse error, an implementation of a parsing location, and implementation of a parsing result. Then this is followed by an object called myParsers. This is an implementation of the abstract trait that I have done in the beginning of the file, in the first part. In this implementation, we implement the abstract parsers trait with the parse error implemented above and the parser implemented above, the parser type selected above. And in here, in this part, we have all the functions, for example, running the parser, slicing the parser, failing a parser, flat map and a few exercises, that these are the functions that they all require the knowledge of a concrete parser implementation to be implemented. So everything we can implement abstractly by deriving operators, we implement directly in the first part, in the trait parsers. Everything that requires insight in how parser is represented, the basic functions, the core API calls, we implement here in this object, which implements our concrete parser. There is a few of those. These tend to be a little bit harder because they are unlike the exercises of previous week, or the exercises in the second part are written not in terms of an abstract algebra that looks the same as streams or prop or par or option, but this part requires insight into our concrete representation of parsers, so it's more idiosyncratic, and I generally find these exercises more difficult. And I mark them as with a plus on the exercise sheet. Now here we enter part 3 of the file. In this part, let's see whether this still tests. Okay, in this part we implement the abstract syntax trait for JSON and all the cases for this ADT. So this is an abstract algebraic data type implementing the abstract syntax for JSON. We have JNOL, JNumber, JString, JPOOL, JRR, JObject. This is pretty much like in my slides. And then we have a class JSON parser that if you give it a concrete parser implementation, for example, my parser is above from second part, it will be able to parse JSON files. This is split into 3 parts: implementing tokens, implementing terminal symbols in the grammar, and implementing the non-terminal symbols in the grammar. So once you have solved all 14 exercises, you can attack exercise 15, which is trying to parse a small JSON file. So this is so much for the structure of this file. The PDF file guides you in order how to fill different parts so that the tests make sense. I will be solving exercise 1, which is in part 2. So I want to spend a few words explaining our notion of parsers. So our parsers, our concrete parsers are functions from locations in the input to results. A result is just a trait that says success or failure. If it's a failure, it carries a parse error, which is a very simplified version of parse errors. We don't do the complex version from the text chapter, it's a simple one. Or a success that carries the value returned by the parser plus the amount of characters from the input that have been consumed by parsing this input. Okay. Now, what is a location? A location is here. It's a very simple implementation of a location or of a cursor in an input. It's just the entire input string. So our inputs are strings, and an offset from the beginning of this, showing how much we have already parsed. Location has 3 helper functions. One is toError, to produce a simple error message. One is to say, okay, move the cursor forward by numCars characters, and one is cursor, which is just a helper function that gives me a string at the current cursor position. So my parsers also has several simple functions implemented, which are pretty much the same as in the slides from the last week's lecture. So in particular, we know how to run this kind of parser. On an input string, we just initiate the location on position 0 and let it run, and then we investigate whether it's a success or a failure, returning left or right. We have a flat map maybe, which is the most interesting case here. Flat map takes a parser and a function from the result of that parser to another parser and returns this second parser. So the type signature is the same as for all the other monadic types we have seen. Since flatmap returns a parser, it has to be a function from locations to parsers, to results. Sorry. So we take a location, we run parser p on the location, and we see what has happened. If it was a failure, we just propagate the failure. One could do a lot more here to make things interesting, to create some stacked failures. I don't do that in this simple version. If it's a success, it means that we obtain a value A from the parser P, and the count of characters that have been consumed while parsing or matching the value A. On that value, we run the function f, which was our argument here, and we obtain a new parser out of it. So now we have to run the new parser on the new cursor. What is the new cursor? The new cursor is the location which we have to advance by the number of characters that were used to match A. Okay. Finally, once this whole thing returns, it gives us a result, and we are using the advanced cars consumed function of result to inform the result about the new characters parsed. So how do I explain it? This call here is going to produce a success value or a failure value. If it's a failure value, advanced cars consumed does nothing. But if it's a success value, that value will say how many characters were consumed to parse with the parser f of A. Okay, so that will be a new number, but it will completely ignore what the parser P has parsed before. So we are adding this number n from here to whatever f of A has used, so that the total result of a flat map is reporting characters used by both. Okay, so this is roughly the design. Now my exercise is exercise 1. And exercise 1 says, well, after studying the implementation of top-level type location and top-level type parser and the structure by parser in parser Scala, try to understand, well, implement the basic combinator succeed that takes an arbitrary value as an argument and produces a parser that always returns successfully with this value, not consuming any input. Okie doke, so this is the exercise. We have a function template here, succeed takes one argument, arbitrary value A, and it has to return a success with that value, not consuming any arguments. So success is a type of, well, it's a parser. Wait a second, it's a parser. The whole thing is a parser, so it should take, it should be an anonymous function from location, here, from location to result, right? So I take a location, I ignore that location, I say I'm gonna succeed, so success with A, and I use 0 characters to get there. And I'm gonna save it and wait for the test results. And the test results, the tests for exercise 1 are failing, so I'll conclude this video. Good luck with the rest.